Right. So what can we say about this function theta naught? Well, unfortunately it turns out, as you would expect, you can't say anything much about it without actually solving the equations of motion, writing down the explicit solution of theta as a function of t and so on. But we can make the following statement. One thing is very clear, that if the amplitude is extremely small, namely if this thing is essentially in a straight line, namely theta naught is so small that sine theta naught can be approximately replaced by theta naught in radian measure. Recall for a minute that if you have an angle theta here, sine theta is found by dropping a perpendicular here, and it is equal to this divided by this base, the vertical divided by the base, that is sine theta. On the other hand, the arc divided by the radius, sorry, the sine, let me write it properly, here is the origin A, B, sine theta is equal to AB divided by OA, not the base but the hypotenuse here, this quantity. On the other hand, the angle theta is equal to the arc. So let us call this C, arc AC divided by the radius OA. Okay. So if theta is extremely small, then this distance becomes approximately equal to that distance along the arc, and sine theta and theta become essentially indistinguishable from each other. On the other hand, the real nature of sine theta is that it starts with theta naught, but there are higher order corrections in theta naught, which is the next leading corrections of order theta naught cubed and so on, which you will learn in mathematics subsequently. But right now the point I want to emphasize is that when this approximation is valid to whatever degree of accuracy you desire, then you can find this f of theta naught very easily, and it turns out that f of theta naught equal to 2 pi in the limit in which theta naught tends to 0. But when theta naught is not very small but is significant, then you need to put higher order corrections in, and you can, as a matter of fact, in this problem find the exact answer in principle, and the answer is going to be something which depends, as you can see, on physical considerations. Whether I have a plus theta naught or a minus theta naught, it does not matter. The angular amplitude is theta naught in magnitude, and it goes from plus theta naught up to minus theta naught on this side. So whether I call this the amplitude or the other one the amplitude is irrelevant, which means that this f of theta naught must be dependent only on the square of theta naught. It cannot depend on the sine of theta naught. So this is equal to some function of theta naught squared in this case, and it turns out that f of theta naught exactly is 2 pi into 1 plus the next term, not surprisingly, will be proportional to theta naught squared over 16 plus higher orders, corrections of order theta naught to the 4 and 6 and so on and so forth forever. Okay. So this leading term being 2 pi is the reason why you write t equal to 2 pi square root of L over G as a standard formula for the time period of a simple pendulum for very small amplitude oscillations. Now how small should this very small be? Well, there is no absolute limit to this, it depends on your accuracy. So it depends on what accuracy you desire. To what degree of accuracy is this true? Well, it depends on to what extent can you approximate sine theta naught by theta naught, and generally if you want like 1% accuracy or something, theta naught must be just a few degrees, but not more than that. There is no specific number like 4 degrees or 6 degrees or something like that, which you might have seen in some places, which tell you under those conditions it is equal to this. There is no absolute number of that kind, limit of that kind. It is a matter of the desired accuracy, as you can see. But that is the best you can do with dimension analysis, and you will agree that it is quite a lot, because I have this extracted this dependence on the parameters in the problem L and G, and I have also shown by dimension analysis the very important conclusion that this time period is independent of the mass of the bob. That is completely gone out of the equation for dimensional reasons, and it has eliminated this parameter altogether. Can we do this sort of trick and solve a little more complicated problem? The answer is yes, and here is one more where this is illustrated, and again it will also tell you what the limitations of the method are. So let us call this, this problem is the problem of finding the terminal velocity in a viscous liquid. And I have in mind the following experiment. So I take a viscous liquid, oil or water or honey or anything like that, and drop a ball bearing into it, a heavy ball bearing, which of course falls in the water, goes down this fashion, it's falling down. And let us say the mass of this object that is falling down is m, and for simplicity let us start by assuming that it is a perfect sphere of radius r. It is falling under gravity, but as it falls there is also a drag force exerted on this ball by the friction from the liquid, and it is called viscosity. As you can see intuitively, honey or oil is more viscous than water. Water in turn is more viscous than lighter fluids, some kinds of petrol products for instance, and these are both more viscous than a gas like air, which also has a viscosity. Every fluid has a viscosity. So the question is, what is the velocity that is reached when the viscous resistive force upwards on this ball is balanced by the gravitational force downwards? We would like to know, is there a terminal velocity, a limiting velocity here? And the answer is yes. And it turns out that in this particular problem, it turns out that the force of gravity downwards is mg, and the force of gravity upwards is given by the following formula called the Stokes formula, and we will come and talk about it again. It is 6 pi r eta, and then v, where this stands for the terminal velocity. This here is called the coefficient of viscosity of the liquid. R is the radius of this ball, and 6 pi, as you know, is a number, pure number. Okay. The question is, where did this come from? So the terminal velocity, the limiting velocity of this ball is mg divided by 6 pi r eta, and we would like to derive this from dimensional analysis. First I have to define what is viscosity of a liquid, and the idea is the following. If you have a fluid layer, if you have a fluid flowing on a tray for example, and the bottom layer is moving at some velocity, and as you go up this fluid is moving slower and slower, higher velocities, because this guy here, the fluid sticks to this glass plate for instance, and then the fluid that is flowing slows down as it comes towards the glass plate till it flows with a certain velocity v here, and out here at any higher point this fluid is flowing at a higher velocity. So there is a gradient or change in the velocity as you go higher up in this pool of water, and in this canal at the lower level the ones that are in contact with the floor of this are flowing at a much slower rate. Okay. Now what happens due to this is that there is a differential in the velocity as you move up in this direction, and therefore if you have a small difference delta v in the velocity, and the velocity here is v plus delta v, as you move up a distance delta x, as you move up further the velocity increases even more, and so on, because there is less friction with the bottom here. This internal friction in the fluid is called viscosity. Okay. And the force due to this internal friction is given by a law called Newton's law. Once again, it is not Newton's original laws of motion, but it is called Newton's law of viscosity, and the statement is as following. If you have two layers of fluid separated by a distance delta x, two parallel layers, one of them flowing with a velocity v, the other one flowing with a velocity v plus delta v here, then the drag force, the viscous drag force is given by a combination of quantities on the right hand side. It is proportional to the surface area of the two planes. So, it is proportional to A. It is also proportional to the manner in which the velocity changes as you go upwards. So, it is the ratio of this difference delta V over this distance delta x. And the constant of proportionality is denoted by eta, which is the viscosity, coefficient of viscosity of the fluid by definition. So, what is happening is that this faster layer is pulling this bottom layer in this direction. So, it exerts a force in this direction on this layer. This slower layer is slowing down the faster layer and is exerting a force in the opposite direction. By Newton's third law of motion, these forces are equal and opposite, and what I have written here is the magnitude of this force. They act in different directions on the two layers. Okay. Now, given this, what is the physical dimensionality of this quantity eta here? That is easy to find, because we know that the dimensionality of a force must be equal to the dimensionality of eta, dimensionality of A, dimensionality of delta V over delta x. But we know the physical dimensions of all these quantities. This thing here is m L t to the minus 2, mass times acceleration. So, another illustration of the fact that a force has dimensions mass times acceleration m L t to the minus 2, independent of what kind of force it is. In this case it is a force inside a fluid, we do not care, it is still m L t to the minus 2 dimensionally. And that is equal to the physical dimensions of eta multiplied by the dimensions of A, which is an area, and L squared. Delta V is L t inverse divided by delta x, which is L itself. So, this cancels out and you are left with the statement that eta must have dimensions m, and then this goes there, becomes L inverse and T inverse. Okay. And it is measured in standard international units in poise. That is the unit. So, when m is 1 kilogram, this is 1 meter, and that is 1 second, this is 1 poise. Okay. And we have numbers, we can measure what this eta is for various kinds of fluids. It is sort of intuitively clear to you immediately that oil must have a higher viscosity than water, honey must have a higher viscosity than oil, and so on. Air must have a much lower viscosity by several orders of magnitude than that of water, etc. So, this is the formula we would like to derive, and let us ask what is the value of what is this V equal to. So, this physical quantity V can depend on the following object quantities. It must depend on m, so we do the same thing as before. We say V is equal to m to the power A, g to the power B, r to the power C, eta to the power D. Mg is a force. So, we have, since mg is what is appearing down here, we should really say force to whatever A. So, we should say mg to the power A, r to the C, B, eta to the D, etc. And now it is a very simple matter to put this in, to put this expression in for eta, the physical dimensions of eta. We know the physical dimensions of r and mg, and show that this thing will indeed turn out to be V is proportional to mg over r times eta. Proportional to, because the constant of proportionality, some constant here, is something you cannot determine from dimensional analysis. We do not know what it is here, but its dependence on the radius and the viscosity is very obvious here. And by the way, under physical considerations, you can see that if you have an object which has got in a fluid which has got a low viscosity, it will move faster, and therefore V is going to increase. It is going to go like 1 over eta, and it so happens that the dependence on the radius also is sitting in the denominator. The smaller the object, the greater the terminal velocity in this case. Okay. So, this is a formula which is derived purely from dimensional analysis. I am not going to do the exact derivation here because it is very, very straightforward, but I want to make some remarks on what this constant is, etc. Turns out that the value of this constant 6 pi is quite tricky. It requires hydrodynamics to establish, and it is not an elementary thing in that sense. You require much harder calculation to do this. Okay. Moreover, you could ask the following: suppose this had not been a perfect sphere, what would happen? Suppose instead of a sphere you had a little ellipsoid of revolution, so that in this direction this axis is semi-major axis, is minor axis is B, and this is A. So you have this American football shaped object, and it is a spheroid or an ellipsoid of revolution, and this has got two lengths here, A and a B, instead of a single R that we had earlier. And I drop this inside the liquid and ask what's its terminal velocity going to be. Well, the point is, immediately you are going to see that this argument breaks down. And the reason it breaks down is that in this problem there are two parameters with the same physical dimensionality. There is an A and a B, both are lengths, whereas in the case of the sphere you had a single thing. For a sphere you just had a single radius here, and that was the end of it, but here you got an A and a B. Whereas here I could say it depends on R, and I put a power of R and try to calculate that power by dimensional analysis. You can't do that here because of the fact that you have both an A and a B, and any ratio of A over B is dimensionless. So this terminal velocity could depend on some unknown function of A over B, just as in the case of the simple pendulum the time period could have depended on some unknown function of the angular amplitude, which was a dimensionless quantity. Here you have two dimensional quantities, A and B, and the ratio is dimensionless. They are both parameters in the problem, and there is no reason why this velocity cannot depend on both of them, but there could be an unknown dependence on some function of the ratio of these two parameters. And that cannot be found by pure dimensional analysis. In fact, you would expect a thing like that to happen. For instance, suppose I said if A is equal to B, then of course you end up with a sphere as before, and there is a dependence here on this R here. This could have been either A or B. But suppose one of them becomes much bigger than the other, A becomes much bigger, this gets much flatter here, etc., more approaching a disk for example, then it is clear that the behavior of that kind of object in this fluid would be very different from that of a sphere. So there is certainly a non-trivial dependence on this F, on this ratio, and it cannot be found by dimensional arguments. Okay. So that is one point. The other point is that this 6 pi, and this formula by the way is called Stokes formula. This 6 pi also depends on some physical assumptions. It depends on assuming that this ball here, as it is flowing down, is such that the fluid here sticks to the surface of that ball, and this is called a stick boundary condition. So it is assumed that the instantaneous velocity of the fluid at the surface of this ball is actually 0. So it is stuck to it, and that is the reason why, relative to the ball, and that is the reason why you get this exact factor 6 pi. If you change this boundary condition as it is called and put in some other condition by saying that the ball slips through the fluid, the fluid does not stick to it, then this 6 pi factor changes to something else. In this case it changes to 4 pi for instance. So as you can see, there are limitations on this dimensional analysis, and the limitations are precisely that it cannot find the dependence on physical parameters if there exist more than one physical parameter with the same dimensionality, so that the ratio becomes dimensionless and the answer could depend on some unknown function of this ratio, dimensionless quantity. So that is a limitation of dimensional analysis, and we have to be careful with that. Now my next illustration is going to take charge of precisely that point. We are going to look at what happens when you have more than one length. Can there be physical arguments to get you the right answer even if you have this situation? And it has to do with again fluid flow, but this time it is slightly different. Let me talk about this. This is called the discharge rate from a pipe. So let's put it this way: how much water can flow out of a pipe. Now of course this depends on the size of the pipe, it depends on the force that is pushing the water through, it depends on the speed with which water comes out, whether the flow is smooth and uniform or whether it is turbulent and so on. So to make the problem precise, we are going to put in some conditions here and see what this flow looks like under those ideal conditions. So I imagine having a container upstairs, an overhead water tank, and then I imagine flow in a horizontal pipe so that we avoid the problem due to gravity being different, putting up the fact that this water will accelerate under gravity. We want to avoid that. And right now I am asking what happens if there is an inlet here. So water is flowing in here, the water flows through this pipe and that is the out. There is of course a pressure difference between this inlet and outlet, which is what is causing the water to flow. There is a pressure head brought in from somewhere else. So let us call this P in and the pressure here P out, and this is less than P in. So there is a difference in pressure between these 2 points, which is what is causing the water to flow out. Okay. There is another physical parameter in this problem, which is the radius of this pipe. So let us call that R, radius. We will make yet another assumption, which is that this flow is smooth and uniform. It is called streamlined flow. So we will assume there is no turbulence, there are no eddies, there is no foam, there is no bubbles, there is none of that, but very slow smooth flow of this fluid such that the path of any fluid particle is a straight line from this end to that end and goes out on this side. Under these conditions, can we say how much fluid is coming out per unit time out of this? It is called the discharge rate, and can we write down a formula for it? So the discharge rate, it is called Q, this is equal to volume of water flowing out per unit time. So it right away tells you that the physical dimensions of Q is the dimensions of volume, which is L cubed per unit time, so T inverse. So we immediately know that it has got to be some L cubed T inverse, that is it, volume per unit time. Okay. Now comes the following question: how does it depend on the radius R? But we can give a very simple argument for this radius R, and it goes as follows. If here is the pipe and here is the outlet, the outer mouth of this pipe, then if the fluid is flowing with a uniform velocity or speed V inside, then it is clear that all the fluid that crosses this area, which is pi r squared, in unit time will come out of this, and that is going to be your Q. So it is immediately clear that if this speed is uniform across, Q must be equal to pi r squared times V. And it seems to suggest that for a given V, this is proportional to the square of this radius. So if you increase the radius by a factor of 2, the amount of volume of water coming out per unit time increases by a factor of 4. Okay. But actually the truth is very different from this. It will turn out that the dependence on this radius is much more severe than just r squared. It will turn out that it goes like the 4th power of this radius. So if you double the size of the radius, then immediately the flow of water is increased, the discharge rate is increased by a factor of 16 rather than just 4. And let us see how that happens. Well, it happens again due to viscosity, the same factor as before, and it happens because the fluid that is in contact, immediate contact with the walls of the pipe are at practically 0 velocity, they are stuck because of the viscosity. On the other hand, the fluid that is in the middle is flowing unhampered at a much higher velocity. So what really is happening is that you have a velocity here in this fashion, and you have a velocity here which is a little less, and then an even smaller velocity and an even much less smaller velocity, etc. So there is a profile, there is a little profile here of this velocity. As a function of the distance from the axis of the tube, the velocity drops. It is maximum at the middle and it goes down to 0 radially on all sides equally. So this formula as it stands cannot be right, and what you need is the V average. So we have to compute what is the average velocity over these various different velocities or speeds of the fluid, sum these averages properly, sum these different velocities appropriately weighted, and then find out what the discharge rate is. And that takes a little bit of calculus, it takes fluid dynamics, and it is not altogether a trivial problem. This problem, by the way, is called Poiseuille flow. The same Poiseuille after whom the unit of viscosity, Poise, is named, a French physicist. And now we would like to find out what is the dependence on this R of this fluid rate, and how are we going to do this using dimensional analysis alone. Well, we need to put in a little bit of physics. By the way, there is one more parameter in the problem, and that is the point I wanted to illustrate earlier, that this fluid pipe, let us say this is the horizontal section of it, and let us suppose the length of this pipe is L. The inlet pressure is P in, the outlet pressure is P out. Okay. It is flowing because P in is greater than P out, it is coming out in this direction. So given this, what is going to happen? What is going to be the dependence of Q on various parameters? Now what are the possible parameters that we can write this down, that we can put in here? Well, the first one is of course R. Q will depend on, it will depend on R of course. It will also depend on of course the average velocity, which I pointed out depends now on the viscosity of the fluid. So certainly there is a dependence on the viscosity of the fluid. And then it will depend on the force that is pushing it, and the force that is pushing it is P in minus P out, the pressure gradient. At every point there is a pressure gradient. This pressure here is higher than the pressure here, is higher than the pressure here, which is why it is being pushed out, and the pressure gradient is delta P over delta X, where X is the distance along the X axis, along the pipe out here. Now this delta P over delta X, if the pressure gradient is uniform across the pipe, this quantity here is, we know what it is equal to P inlet minus P outlet divided by L, the length here. If the pressure gradient is exactly the same at all points, then this must be equal to this difference divided by the length of the pipe L. So you see what has happened is that even though we have two quantities of dimensions length, one is a little l and the other is a capital R, and the combination of these two, the ratio of these two is independent of dimensions, has no dimensions, and therefore there could be some unknown dependence on a function of R over L or L over R. We got over that by the physical argument by saying that the L dependence is going to come in the pressure gradient here, and that is sitting here in this case. So I treat this as a unit, this as a unit, this as a unit, and now ask what is this discharge rate going to be like. And that is now a tractable problem, because I immediately see that I need the physical dimensions of all these fellows. The dimensions of R of course is length, dimensions of eta, we wrote that down earlier, it is M L inverse T inverse here, and then delta P over delta X. What is the physical dimensions of this quantity here? Well, pressure is force per unit area. So this is M L T to the minus 2 over L squared, and then a delta X is a length. So there is one more L out here, this cancels, and this is equal to m L to the minus 2 T to the minus 2. Okay. And now we are all set, because all we have to do now is to say that this Q is proportional to, on this side, r to the power a, eta to the power b, and delta p over delta x to the power c. And write down our equation, which is L cubed T inverse must be equal to L to the power a, eta to the b is m to the b, L to the minus b, T to the minus b, and then delta p over delta x to the power c, which is m to the power c, L to the minus 2c, T to the minus 2c. So this whole thing, combining everything together, is L to the power a minus b minus 2c, m to the power b plus c, and then T to the power minus b minus 2c, and that must be equal to this. So we have a simple set of simultaneous equations. So it's b plus 2c must be equal to 1, that is this thing here. Then b plus c must be equal to 0 out here, and a minus b minus 2c must be equal to 3. And all we have to do is to solve these three equations together, and that is a trivial thing to do, and you have a unique solution, and the solution turns out to be, and this is something left to you as an exercise, the solution turns out to be the following: Q is proportional to r to the power 4. So this coefficient a, this number a, the index turns out to be 4, and then it is proportional to delta p over delta x, so it will turn out to be p2 p out p in minus p out divided by L out here, and then there is an eta in the denominator, okay. And that is the formula. This constant, once again, in this case it turns out to be something which is proportional to pi over 8 or something like that, some number, some pure number. This quantity here, this dependence here, r to the power 4, says that if you give me a fixed pressure head and a length of tube, a fixed length of tube for a given fluid under these conditions of Poiseuille flow, then the discharge rate is proportional to the 4th power of the radius. And we got this answer in spite of the fact that you also had another length in the problem, and therefore potentially there could have been some function of r over L or L over r in the formula, which did not happen. We have got this out explicitly by saying, look, the argument was a physical one which said depends on what the pressure difference is, pressure gradient is, and this appeared only in the pressure gradient here. So in this sense we have been able to circumvent this problem of more than one parameter with the same physical dimensions and actually extract the formula out. And it is quite a surprising formula that there is a 4th power here. So it really says that if somebody quietly doubles the inlet pipe radius, then he or she gets actually 16 times as much water. The discharge rate increases drastically. So this is therefore a very, very sensitive quantity here. Now whenever you have formulas of this kind, what you ought to do is to try and graph these formulas. You ought to see if it makes physical sense or not by plotting these things. For instance, if I plotted Q versus R as a function of R, keeping the other things constant, this 4th power increases very rapidly. It is very flat here and increases rapidly. If I plotted this Q as a function of eta, for example, the viscosity for different fluids, then this thing goes like 1 over eta, goes down in this fashion. Similarly for the length and so on. Now again, this formula is derived under very, very specific assumptions. You want a length which is much greater than the radius, you do not want a very short pipe, then turbulence sets in, various other things happen. You want streamline flow, you want a constant pressure gradient and so on. So under all these conditions of Poiseuille flow, this is the formula for the discharge rate, which we found without too much difficulty using just physical arguments. So this is the power of dimensional analysis, and we will have occasion to look at other examples as we go along.